All right, so let's start with part 2 of the lecture for today. And we're going to continue right where part 1 left off and talking about disaccharides. And disaccharides are the simplest polysaccharides you can have, being units of 2. And when we talk about disaccharides, the way we talk about them is how they are connected to each other. So let's look at the disaccharide lactose. Lactose is made out of 2 sugars, galactose and glucose. And their connection is called a beta 1,4. So let's take a look at how we get beta 1,4. So our first atom in the glycosidic bond is an anomeric carbon because it's connected to 2 oxygens. And the way that this bond is being written, this glycosidic bond, is that it's going up first. So that means this OH was originally pointed up. Then we see the CH2OH on the same ring is also pointing up. So they're both going in the same direction. So it's beta. And then the other glycosidic bond is at the 4th position. So that's why it's beta 1,4, saying what carbon is connected to. And if it's an anomeric carbon, you say if it's alpha or beta. Note here, the glucose is in beta conformation 2, but we do not include that unless the anomeric carbon is in a glycosidic bond. The reason is, if you remember on Wednesday, when we first talked about cyclization, this ring sugar can reopen up to be linear. So this beta is not set in stone. This glucose could open up and this could go to alpha. It is possible to do that. So since it's not set in stone, we don't list it and we only care about the connection. Compare lactose with sucrose. So anomeric carbon here, the bond is going down and then the CH2OH is going up. So they're opposite directions. So that's alpha, that's carbon 1, alpha 1. And B, OH, O, so that's an anomeric carbon. The OH was going down. The CH2OH is going down, so that's beta. So this is alpha 1, beta 2. So our glycosidic bonds, or rather our anomeric carbons, are both in the glycosidic bond. Therefore, we need to list alpha and beta for both carbons. All right, so here's some practice to name our linkages. So I'll pause, take a minute, and see if you can figure this out. So let's take a look here. So the first thing you should do is figure out where the anomeric carbon is. So right here, so the anomeric carbon in a 6-membered ring is 1. And where's the anomeric carbon here? Well, it's right here. So this is carbon 1. And then to number the carbons, you just go away from the oxygen. So here's 1, 2, 3, 4. So this is a 1,4 linkage. And since the 1 is an anomeric carbon, we have to see if it's alpha or beta. So it's going down here, but up here. So they're opposite directions. So that's alpha 1,4. And this is reducing because you have a free anomeric carbon right here. So that's A. B, anomeric carbon. And then this is an anomeric carbon. So this is 1. So it's going to be a 1 dash something. This is going up. This is also going up. That's beta 1. And then we have to see what's the other linkage. So 1, 2, 3, 4. So this would be a beta 1,4, reducing because the right sugar, the anomeric carbon, is not in a glycosidic bond. So let's take a look here. So anomeric carbon here, oxygen, oxygen, anomeric carbon, 1, 2. This is 1, up, up. So that's going in the same direction. So beta, 1, 2, reducing because you have a free anomeric carbon. D, anomeric carbon right here, anomeric carbon right here. Now, in the 5-member ring, the CH2OH off of your anomeric carbon, if you remember, is number 1. So this is 1, then 2, 3, 4, 5. Carbon 6 is the one in our glycosidic bond. This is carbon 1. So this is our anomeric. So this is pointing down. This is pointing up. So that is alpha 1, 6, reducing. And E, anomeric carbon, because it's 2 oxygens. And here we aren't in a cycle, right? So we don't have an anomeric carbon. In truth, the anomeric carbon should be this one because it will form the attack, but it's not an anomeric carbon yet because it's still linear. So our numbering, this is carbon 1. The OH is pointing down, or the bond's pointing down, because remember, if it's a skinny line and then you have a line like that, so the skinny line means like in the plane, the H is coming at you. So that's why I'm using the down notation here. While our CH2OH has the wedge, so we're pointing up. So they're going in opposite directions. So that's alpha 1. And then our numbering scheme, so for a ketone, which is what we have here, the CH that's near the double bond, that's 1. So that's 1, 2, 3. This is alpha 1, 3. The anomeric carbon's open, so this is alpha 1, 3, reducing. So if you have questions about that, please do let me know, and I can always help you with that or give you possibly more practice as well if you want to ask for that. Now, let's look at some common polysaccharides that are used inside of our cells. Now, let's start with cellulose, which isn't used in our cells, but it is used in the cells of a lot of organisms. So what cellulose is, it's glucose monomers that are linked up in a beta 1,4 linkage. And these are linear, so you don't branch. So it's just a straight line that can be up to 15,000 glucose residues long. And with these, the reason why it is so sturdy is because these can form ribbons, flat sheets, flat ribbons. And then between these ribbons, you have hydrogen bonds that are holding these ribbons together. So that's what makes cellulose so strong, is that you have these hydrogen bonds between these sheets holding everything together. And we can't digest cellulose, but there is an enzyme that assists to do this. It's called cellulase. And so cellulase, which is found in some bacteria and in termites, the termites have the bacteria in their guts, which is why they can break down cellulose. Cellulase will break down that linkage. Mammals, we can't, unless you have that bacteria, like cows have that bacteria in their rumen. Now, chitin has the same linkage, beta 1,4, but they are a slightly different sugar. They have this acetyl group here on position 2, and that makes N-acetylglucosamine. So it's basically glucose with this little addition. And that little addition makes that hard chitin that's found like on beetles and other insects, makes that very hard shell. And the only difference between chitin and cellulose is just this amine substitution. All right, so here we have the next problem. So for the following, if you remember, cellulose is beta 1,4, and try not to look on the picture on the previous slide when answering these, because this is a way to really test yourself to see if you understand the information. So let's say we take cellulose and we add methanol, and methanol will methylate the free anomeric carbon. How many methyl groups will be added per cellulose chain? So to really understand this, you have to understand what the linkage is. It's beta 1,4, and it's just continuing. And how many free anomeric carbons will you have? Well, every glucose will be bonded to its anomeric carbon because of that beta 1,4 linkage, except the very last glucose. So let me draw that. So that's carbon 1, 1, 2, 3, 4, 5. Sorry, that's a very bad drawing. So the last glucose is going to be connected at the 4 position because of beta 1,4, but it won't have another glycosidic bond because it's at the very end. So that's why it has a free anomeric carbon. That's why you'll have one methyl group per chain. Now B, let's take a look at this. For cellulose, now we add dimethyl sulfate, which adds to all free hydroxyl groups. How many of these will be added other than the first and last glucose? So if we look, I know I said not to look on the previous page, but it's way easier than me doing these really bad drawings. So if we look at cellulose, right, how many free OHs do we have? 1, 2, 3. Because the 1 position and the 4 position, the OHs are bond and are glycosidic bond, so they're not free. So we're going to do 3 substitutions for 2B. Right. So let's continue on with polysaccharides, and now let's look at alpha amylose, which is just glucose in alpha 1,4. So cellulose was beta 1,4. Amylose is alpha 1,4, and that little change in how the glycosidic bond is oriented makes all the difference, right? So amylose makes up one part of energy of plants, makes up starch, right? And starch is what we eat, right? So starch is made out of 2 things, amylose and amylopectin. And both amylose and amylopectin has alpha 1,4 linkages. The difference between the two are branch points. So if we look on the image to our right, the blue is amylose. This is just linear. However, amylopectin has branch points as shown here. So they have alpha 1,6. So normally they are connected alpha 1,4, alpha 1,4, alpha 1,4. But every so often, one glucose will have an alpha 1,6 and start a branch point somewhere else. And the reason for this is quite clever. So starch is the glucose storage supply for plants. And to release the glucose, plants have an enzyme in them that chops off glucose from the non-reducing ends only, right? So if you look at amylopectin, it has exactly one reducing end because of the branch points. And it's like what we talked about on cellulose, right? On the last problem, we said cellulose only has one free anomeric carbon. Same thing with amylopectin. But since it's branched, it has many, many, many non-reducing ends. So if a plant is starving and it needs to release energy from that starch, and if it works from the non-reducing ends, it can start chopping off glucoses from many different points and release a large amount of glucose in a short amount of time. If it needed to work from the reducing end, however, it would be very slow because it would only have one glucose that could be chopped off at a time until it got to a branch point, then it could start there as well. So that's amylose and amylopectin. And that's also the logic of why amylopectin is the way it is. So that's the plant storage starch. Mammals, we have something similar, called glycogen. That's our storage system in animal cells. And it's usually in your skeletal muscles and your liver. 10% of the weight of your liver is due to glycogen. And glycogen is very similar to amylopectin in that you have alpha 1,4 glucose connections. And you also have alpha 1,6 branch points. The big difference is, though, is that glycogen is much more highly branched than amylopectin. So you have a branch point every 8 to 14 residues in glycogen. And again, the same idea presented here we saw in starch. You have these branches because you want to increase the amount of non-reducing ends, because the way that our enzymes work in our cells is that they take off glucose from the non-reducing ends. You also have a debranching enzyme. So we'll go, if you take biochemistry 2, we'll go over this mechanism in much greater detail. But basically what happens when you're chopping off glucoses, when you come to one of these branch points, you have to stop, and a new enzyme called a debranching enzyme will basically break off the branch. And once that alpha 1,6 bond is broken, you can continue to chop up your glucose. But yeah, like I said, you would go over that in biochemistry 2 if you decide to take that with me. So here is another problem, just to check your understanding if you really know what's going on for how these glycogens are created. So how many reducing ends are in a molecule of glycogen that contains 10,000 residues with a branch every 10 residues? So this might seem complicated, but it's 1. For every single glycogen molecule, just like amylopectin, just like cellulose, you just have 1 non-reducing end, because all the other anomeric carbons are in that alpha 1,4 or alpha 1,6 bond. There's exactly 1 glucose at the very end of the chain that the anomeric carbon is not in a glycosidic bond. And B is amylose or amylopectin, to be more likely to be long-term storage. And that should be amylose. Let me just double check the picture here. Yep, so amylose, if we go back to this picture, remember I said you can only take from the non-reducing ends. So imagine we have this very long amylose, even longer than this. And when I want to take off glucose, I can only do it 1 at a time because I have to take it from 1 end. Amylopectin, though, I'm taking it off multiple ends. So amylopectin is like a very fast supply of glucose, but you'll use it up quickly because you're chopping off a lot. Amylopectin is your fast release. Amylose is more your slow release, where I can only chop off 1 at a time, but it's going to be a steady rate. So that's why it's your long-term storage. Now, the last thing we're going to talk about today are glucosaminoglycans. And let's break down what this word actually means. So glyco, so that usually means like sugar or glucose. Amino, well, that's like nitrogens. Glycans means sugar. Right. So what these are, they're glucose with amino substitutions that are forming sugar units. And these long polysaccharides, these glycosaminoglycans, they come in just repeating disaccharide units. So for example, for hyaluronate, it's these 2 molecules repeating over and over and over and over and over again. Now for these, I don't want you to memorize the exact structures, but what you should know is that for glycosaminoglycans, they have some common things that are going on. One, they usually have this amino group at position 2. And 2, they're very negatively charged. And they are unbranched. Long linear sugars that are very negatively charged with these nitrogen groups. And you usually find them outside the cell, extracellular space. So your connective tissues, collagen, and other proteins are usually embedded in these. They will create like the cushion of your knees, for example, are glucosaminoglycans. Very slimy, very mucus-like, high viscosity and elasticity. And the reason for these is that, since these are very hydrated, since they attract a lot of water, what happens for your knees is when you compress, the water will kind of like go away, but these things are incredibly negatively charged, so they will repel each other. And that's kind of like cushion for your joints. That's one way that glycosaminoglycans actually work. And that's why if you have deteriorating joints, your doctor might ask you to start taking these glucosaminochondroitin supplements. It's basically these sugars. So here, the last problem for today is just, again, to try and check your understanding of what these is. So what is the net charge of a chondroitin 4-sulfate molecule that has 100 disaccharides? So chondroitin 4-sulfate has one disaccharide has a -2 charge. So if you have 100 of those, that's minus 200. And B, basic fibroblast growth factor binds to the glycosaminoglycans in the extracellular matrix. What amino acids are there? Well, if these are negative, I would expect positive to bind, because positive and negative attracts. That would be your R and your K. Right, and with that, that's the end of today's lecture. Again, if you have any questions, please do not hesitate to ask. Again, and I apologize for not being able to have the live lecture today. But other than that, I'll put up a homework like always, and hope you have a good weekend. And we'll see you on Monday, where unless something else happens, I should be able to have the live lecture. All right, see you then.